First of all, let me start with saying that it is my great pleasure to be here, and I'm very thankful to the organizers for putting together this this amazing workshop with the topics I've been really interested in lately, and it's great to see all this new research coming out, and it's also a great opportunity to connect with other people and to see how where the field is going, right? Okay, so the topic for today is techniques for making locality sensitive hashing adversarially robust, right? And the application is nearest neighbor search. And right, so let me start from something that's probably already established in this workshop. So there's quite a bit of delay, which is that randomness is extremely useful when it comes to big data algorithms, and often it's completely unavoidable. Right, like for instance, when you think about streaming algorithms, you've seen those here before, right? If you get rid of randomness, if you are in a totally deterministic setting, then for many problems it is known that you cannot do much. In the sense, you have to essentially store the entire input, right? There is no way to compress it into something smaller that is sufficient with high probability for any input to work, right? So this is impossible for randomness, right? So randomness is really crucial. And the problem, and it is great, right? But the traditional way randomness has been used or analyzed in these kinds of settings is that you assume if it's some kind of dynamic data or a stream or something, right? You assume that the whole sequence of updates is fixed in advance. Okay, so if you assume that the sequence of updates is fixed in advance, then in many cases it is very easy to make this work in this setting, right? Because standard amplification techniques usually work, right? Like for numbers, you can take if what you're supposed to output are some estimates, then suffices to output like the median of multiple estimates, and that improves the probability of success, and you're very likely to be good. For instance, at every step throughout your stream, you're very likely to output a good estimate, right? You're very likely to make everything work. Well, not just a single query, but all the queries, all the estimates you're supposed to provide throughout. Right, and if it's not the number, then usually you have to look inside the algorithm, right? You cannot just take the median of decision trees, as one student insisted in some course I was teaching, right? You cannot just take the median of decision trees because they're incomparable. But usually it's very easy to look inside and amplify the probability of success. Okay, yeah, so these are some examples. I already mentioned some of them, right? Like you've seen talks on those topics yesterday, right? Like any streaming algorithm that continuously provides estimates, that would be one example of this kind of application, right? Any frequency estimators, count sketch, count mean sketch, and these are other examples of these types of data structures that are traditionally analyzed in the setting where the sequence of updates and queries is fixed. But the problem we're going to be focusing on today is near neighbor search, right? Via locality sensitive hashing. So this is a very classic way of approaching near neighbor search, and unfortunately, it's vulnerable to these kinds of attacks, right? So first of all, why do we care about these kinds of attacks, right? So there are, I think, two main reasons. One of them is, what if someone wants to actively break your algorithm, right? And this person can provide updates, make queries that lead to incorrect results, right? So that would be one example, right? There's someone who actually wants to break your algorithm. But there is also another scenario which I think could be is very practical in many settings. What if you have this nice randomized algorithm that you want to use as a subroutine to some other algorithm, right? When you use something as a subroutine for something else, it is often the case that your queries or updates are going to be adapted. You learn something about your input, about the data you're dealing with. And using that information, maybe you provide some additional, you create some additional updates, right? And make different queries. So these are some of the problems you have to face. Question?
I mean, it wouldn't be like necessarily like adversarial, right? Like it would be like interdependent in a way. But...
Right. So it's not adversarial. So that's why scenario one is an adversary, and scenario two is someone who maybe doesn't have bad intentions per se, but it could just happen accidentally. Right, it could still happen, right? Like there was a great example in one of Amit's papers, which was for those who know what this problem is, but L0 sampling, and in particular, you can use it as a subroutine for extracting spanning trees, right? So suppose you extract a spanning tree, so data structure knows about these edges, maybe it doesn't know about all the edges in some sense, but now you remove these edges. And you ask the same query, right? Because like maybe you want to partition the whole graph into multiple trees, right? Or forests, right? And unfortunately, at some point it has to stop to work unless you keep the information about all of the graph, right? So there are cases where this could happen, right? Yeah, I suspect in many cases in practice, you're kind of fine, and people will probably use these things even though they could break, and often probably they're fine. But if you want to be sure that they work, you have to be careful. Okay, so nearest neighbor search and using LSH, right? And there was this very nice paper by. So we were thinking about this problem before, but there was this very nice paper by Kapralov, Makarov, Zoller, who showed that actually it's possible to break locality sensitive hashing. And my goal is not to go. It's not my goal to go here into details, but the idea is that. Like in the very simple setting, they had one isolated point, and locality sensitive caching internally uses hash tables, and they were able to figure out which coordinates of the points in the Hamming space this thing uses, and they were able to craft a point on which the whole thing was breaking. Right, it was supposed to report a new neighbor who was somewhere nearby, but all these hash tables thought that this was not something unrelated. And it was not reporting that point.
So is this for heavy distance or like for geometric?
Their presentation was for Hamming distance and the Hamming cube, hypercube, right? Good question, right? So because it's like very hash function dependent, so it's a good question. Like if it would be easy to adopt it to some other metric spaces and some other types of hash functions. So good question. I didn't think about this. I'll add this to the open problems. Okay, good. So right. So this was a very inspiring paper, like the things they were doing, right? And since then, there have been some lots of not maybe not lots of, but there have already been some attempts at making locality sensitive hashing work in this kind of setting, with the purpose of near neighbor search. And in particular, I should mention this paper by Feng et al. Right, that includes two people sitting here in the front row and maybe some other, I just don't know them. So basically they I'm gonna be explaining the question in a second, but they ask essentially the same question in some sense, right? Which is how to make this work in the adaptive setting, how to make LSH work in the adaptive setting. And because there's a huge difference between like search problems and classical estimation problems. This is something I'm going to be explaining in a second. And they provided some solutions that work, for instance, if you have like sparse neighborhood. If you don't have too many points, I hope if I correctly understand your point, there aren't too many points around your query, you're fine. Right? The thing is, so this probably works in lots of practical settings. One problem is that it assumes that it has to make some assumption, right? There are too many things around to work efficiently. So it also assumes that maybe someone making queries only controls the queries, but not the dataset, right? And what I'm going to be showing is going to work for any dataset. So we can allow the adversary to select the dataset as well. Okay. And was another question?
I mean, it's just that, but I guess it's better if, you don't do this. So I'm gonna ask, can you explain a little bit better, LSH,
Yes, so I'm gonna be talking about this in more detail.
Faster.
Yes.
But, I imagine you have a lot of things to talk about.
Well, I can stop it. I don't have to go to the end of the talk. I'm happy to stop earlier. I'm gonna be talking about LSH in a second, right? Definitely, it will require more time to explain LSH and how exactly it works, right? So it's kind of meant to be high level, but I'm very happy to talk about this offline, for instance.
Yeah.
Give you examples. Like,
Yeah, I think that's
Yeah,
fair, you know.
yes.
I don't want to like slow you down.
Mhm.
Thing.
No, that's fine. Ask questions. I guess I started 10 minutes late, so I shouldn't be taking too much time, right? But like, I'm happy, to like, I'm not an expert on LSH and near neighbor search, but I'm happy to do like a simple tutorial in the spare time if someone wants to learn more. It's okay. That's the advantage of having a workshop, right? Versus some conference or something, right? And there was also this paper by Bateni et al. Who were using nearest neighbor search as a subroutine for their hierarchical agglomerative clustering. Right. So for those of you who know what hierarchical agglomerative clustering is, the queries are definitely adaptive, right? Because you learn something from the previous queries, like you look points that are nearby, you connect them, you put them together, and then you make new queries, right? And you keep going. Right. So this is like an example where maybe you are not trying to break things on purpose, but it could just happen, right? Right, and what they use there is kind of similar to like the last method I'm gonna mention, which is like making sure that like if the dimension is low, you can kind of amplify things, and unfortunately this like requires the size of the data structure to grow by a factor of the dimension, so that's kind of slow. But for high dimensional spaces, that's not good, right? But that's what you can do. Okay, so let me state the model. So you kind of already maybe, so for those who were here yesterday, so I guess not David. Oh no, actually David wrote the service. He knows this work very well. But we're gonna be essentially working in this adversarial robust algorithms model of Omri, JRM, David who is here, and Yov, right? So this is the model we're going to be using, right? So you can think of this as having two players, right? One player is the algorithm. In our case, it's going to be the nearest neighbor near neighbor search data structure, and the other person is the adversary, right? And the adversary, in our case, we're going to assume that we have a static data set that the adversary can give us. So it can be whatever it can be, right? So the adversary can give us a data set, and later, the adversary is going to keep making queries. So the adversary doesn't see randomness inside our data structure. So at this point, without going into details, it uses some hash functions which are selected randomly and puts things into buckets, right? And in general, the hope is in the adaptive setting that if some points are close, they're going to end up in the same bucket. But here, the adversary is going to be learning something about the data structure, right? And in the end, the adversary is going to win if at least one reply to at least one query is in some sense not good enough. In our case, it's not gonna report data a close near neighbor when there should be one. Okay. Right. So basically, what we want is the algorithm to always give correct answers. Okay. Right, and in general, apart from the works I mentioned and some other works that explored like some graph problems, the main focus of this research, especially when it comes to like streaming and whatnot, was on estimation tasks. Right, so you're supposed to output one number, right, and beyond this original paper that introduced scale switching, so assuming that things kind of grow and they don't change too much, right, you can just put a small number of oblivious algorithms and use their estimates to provide a good answer. There is like it's a really nice idea, very nice scale switching technique, and it's very simple. At the same time, the proof is slightly subtle. So like if you don't know it, I encourage you to look into this, to read this paper. And what is very important for the motivation behind this paper is this other paper by Avinatan and multiple people, including Uri, right? So they introduced, so it seems like if you can hide what we are doing from the adversary, things should be fine, right? Things should be fine. So, and it's kind of like a natural question, like, maybe we can use differential privacy somehow, right? And this is actually what they figure out how to do, right? It's a very beautiful paper. The idea is that you take roughly square root of Q. So if you are supposed to handle Q queries or Q estimates, you are supposed to provide Q estimates, then you keep roughly square root of Q independent copies of your like oblivious traditional data structure or algorithm. And then you use differential privacy, like for instance, you can put the differential in private median, or there are some other things you can do to output the final estimate based on the estimates from all these copies of the algorithm. Right, so basically the idea is that this comes with an overhead of square root of Q, right? And the nice thing is it works for pretty much all estimation questions. Right, and that's very nice. Unfortunately, right, it's not applying to search problems. So in search problem, you're supposed to output like some specific object, right? So for instance, the near neighbor search problem, you're expected to output the point from database. You can like make up a data point. Well, who knows? Maybe with large language models, generative AI, you could somehow get around this, right? Like output fake person that's gonna be telling the adversary what's inside your algorithm. The other problem is the set of options is large. If the set of options was small, you could kind of like sample all of them and sample from them to the output, so the adversary wouldn't learn much, right? So unfortunately, the set of options could be large, and whatever you output a specific point, like you don't control how much information it reveals about what's inside the data structure, right? It could be telling the adversary quite a bit, right? And because this is a search question, we are supposed to output one of the points. There is no easy way to hide the randomness, right? You cannot take a private median of multiple points, right? Especially if you're expected to output an actual data point, right? Because someone is going to be doing some research on this data point, right? So that's the problem, right? So that's the main question, right? Is there still a way to deploy these differential privacy techniques to obtain maybe an overhead of square root of Q, right? In space over Q queries, let's say, right? Of the data structure. Right, and the question is, so can we get close to this with like fast queries still? Question?
So I mean, like, I guess like this doesn't apply to like any case, but like, if you have like an Euclidean space, like, could you perhaps maybe like return like something that had like less precision, so you wouldn't exactly know, you would like like your point is around something like
that. So that's a good question, right? Like the question is what you're actually planning to do. Right, because like traditionally you're actually supposed to output something in the data set, right? Because like imagine a scenario, someone wants to see, okay, my patient has these symptoms, right? This kind of made up example, but I think it makes sense that you have a patient with this set of symptoms and you want to find someone with similar symptoms, right? You don't want like a fake person. You want an actual patient that existed before with the same symptoms and maybe see what worked for them, right? Or so there are good reasons often why you want an actual point versus something that hides what the algorithm is actually doing. Yeah.
Yeah, but like here, if you really want it to be the one subset of data, and then like what if my nearest neighbor is like here very close, and the all others are like like 1 billion approximation, which is like not within your approximation budget. So
you want to output that specific point.
But then in this case, like there's no way to hide the randomness of the internal.
Yeah, so you don't hide randomness. But like I mean, okay. Actually the randomness is here hidden perfectly because there's only one correct answer.
I see.
And you always give the same answer. So
I see.
So the adversary doesn't have anything, right?
I see. So is there a lot of points like near the optimal that you can hide, otherwise
yes, if it's just a single point, that's easy, right? So like the example that's exactly like an example that was in the Krapramov et al. Paper, right? And that they had a single point. So like if it's a single point, then it's easy kind of to hide to make this work for a single point, right? And like the paper by Samson and David and the co-authors is kind of extending that to I guess like good neighborhoods in some sense. Okay. So there is the long requested quick review of near neighbor search. So unfortunately, I won't be able to go into details, but let me first state at least what the problem is, right? So the usual setting is as follows. So you have some set of points, let's say n, some metric space, and you're gonna have two parameters. One is some radius, and c is some approximation constant. And what are you supposed to do in this problem, right? So on some query queue, so this is the point Q, the query in the middle, you are supposed to, if there is something in the smaller circle around it, the circle of radius r, you are supposed to output something from the bigger circle. Right? And so if there is nothing in the bigger circle, like you're always going to output nothing, right? You won't find anything. If there is some, it could be the case, but it could be the case that it's hard. Maybe there are some points in the smaller circle, but the number of points in the that are outside the smaller circle, but in the bigger circle is so big that it's like hard to find between them the points from the smaller circle. Right? So in general, if there is something in the smaller circle, we request that you return something from the bigger circle. In particular, sometimes you might return something from the bigger circle, even if there is nothing in the smaller circle, and that's fine. Right? So this is kind of like this approximation factor of. Okay, I think I have like 10 minutes. So let's. Right. So basically, the main idea behind locality sensitive hashing is that you have some nice neighborhood preserving hash functions, a family of hash functions, such that if 2 points are close to each other, then they are more likely to end up in the same bucket in your hash function. When your hash function maps points to buckets, and if they are far, they are less likely to land in the same bucket. And I don't want to go into details here. I'm happy to discuss them later. But basically, what you do then is you put multiple of those hash functions together to make sure that anything from the bigger circle is unlikely to end up in the same bucket as your query point, whatever your query point is. Right? So at this point, it's good. You are not likely to see too many of the far points, which you don't want to deal with them. Unfortunately, it also makes the probability of good points smaller. So there might be good points that because of that, the probability decreases. So what you do then is you have multiple hash tables, and you keep looking to those hash tables until you find a near point or you find nothing. Right? And with setting the constant, and in general, it's possible to compare your query point to only roughly n to the row point for some row between 0 and 1. So it's sublinear in the number of points, right? You don't compare yourself to all the points, which would be a very natural solution, like the brute force solution, but would be very slow. Question?
So like my understanding is like if we return something from the bigger circle, that's fine, right? Or is it like we prefer something from the smaller one?
Yeah, just return something from the bigger circle. Just there might be hard to find things which are exactly in the smaller circle.
Okay.
Yeah, that's in general. It's like it's a difficult question, right? Because like imagine, just intuitively, without specifying how this function, how hash function exactly work. Imagine you have one point that is very close to this border. There is like 1 million points outside of this border in the same place, essentially, right? Like they are very likely to end up in the same bucket in your hash function, and like finding the single point that is close would be difficult. That's the general intuition. Okay, so this is how LSH works, right? So let me try to sketch at least simple ideas, like the main ideas behind how to make it adversarially robust. So the first observation is the decision version of the problem is easy, right? So suppose that you don't return a point, you're just supposed to answer a yes/no question, right? You're supposed to return true or false. So if there is a point in the smaller circle, you are supposed to answer true. And if there is no one in the bigger circle, you are supposed to say false. Right? It could be the case that there is someone in the bigger circle, but no one in the smaller circle. So then you can answer whatever it is, right? So this is the decision version, right? So okay, so this is not a numeric problem. It's 0 and 1, but it's actually the same. So it's easy to make this adversarially robust by maintaining roughly square root of copies of a data structure that answers this, right? And then privately aggregating what they tell. In particular, you don't have to look at all the square root of Q copies. You can sample like a small number of them and just look what's the majority in your sample, and that suffices. Right, so you can solve the decision version of this problem easily, right? And just to mention, so how to use the standard LSH to solve the decision version? You just do the search. If you find something close, if you find something, if it returns something, then you reply true. Otherwise, you reply false. Okay, so it's very easy to switch to the decision version from the search version, and the decision version is it's easy to make it adversarially robust, right? So how can we use it in like in some sense very simple way to create something that's adversarially robust? So the idea is, you know, take your data set and partition it into roughly same size k groups for some k. And you create a robust data structure for the decision problem on each of those groups. Right now, when the query arrives, what you're gonna do is, so there are, you know, some slightly potentially faster ways to do it, but suppose you're gonna run this query on each of those groups. And if this adversarially robust version says true for some of those groups, you just do exhaustive search on that group. Right? You just compare yourself potentially to all the points there. Right? And this is adversarially robust because, you know, these things are independent. It's completely independent randomness. And the decision version is adversarially robust. So like even if you publish the full vector of true and false every time you give it to the adversary is not likely to break it. Right? And if there is a point that is in the smaller circle somewhere in particular, I mean, so first of all, you will never get false. You are very unlikely to get true if there is no point inside that is close to the query, right? Because like this, you can make it as impossible because when you return some point, you can check if it's actually close. If it's not, you're gonna treat it as a no. Right, so if you get that true from some of these groups, there is gonna be something that is in the bigger circle there, and also if there is something in the smaller circle somewhere, you're always gonna get true with high probability for that specific group.
Yeah. How do you select those groups? Like, is it
Yeah, so the groups you assign them, you create them arbitrarily. You just partition your data set into small parts. Right?
So do you need to hide the randomness from this?
Oh, like how you partition things into groups? No, that could be public. That could be public. Like the adversary shouldn't be able to let them. Okay, so this is very simple, right? And you know, so what's the processing time, the pre-processing time, the space usage? So I'm ignoring here like the time that computing hash functions or distance computation requires. But for instance, you know, so this is gonna be the space complexity, and the total pre-processing time is gonna be of this order. So you get this factor of square root of q. And then it's gonna be times 1 plus rho. So rho is what we had before, but it's gonna be divided by k to the rho. And the query time is gonna be roughly this, right? So if you want to optimize your query time, then you can select it such that the space and pre-processing be kind of roughly, you know, that's the complexity. You get this factor of square root of q, and the query time is n to the 1 over 2 minus rho. Right, so this exponent, you can see that whatever the rho was, because it was some number between 0 and 1, now this exponent in the search time is going to be 1 over 2 minus rho, and that's going to be something between 1/2 and 1. Right, so it's still going to be something here. You're not going to be looking at all the points. Okay. Right, and you don't even need this square root of q time in the query. Right, but it's unfortunately there in the pre-processing because you have to create those square root of q copies of like some, you know, the decision version, right? So that's the solution one, which is very simple. In the remaining 1 minute, let me talk about a slightly better solution, potentially better solution, right? So the idea is, so this is kind of similar to the question that was there, right? Like suppose that I always reply with the same point, right? But it's the only point that is correct that doesn't tell the adversary anything. So imagine a slightly broader set of allowed outputs, right? So suppose that there is some number of outputs that are allowed, and I always output one of them uniformly at random, right? Like if I could do that, that would also not tell the adversary anything, right? Because it's just uniformly random, right? Right, so this, in that sense, this idea would, like, if you can implement this idea, it would not reveal anything to the adversary. And this is where we want to use the fair neighbornet framework, which was created by a number of people, right? And basically, the idea is that if you have an LSH instance, you're supposed to output something uniformly from the smaller circle, and you're only guaranteed that this is gonna work fast if the ratio of things in the smaller circle to things in the bigger circle is small. Right, so that's the only time you're guaranteed that this is gonna work fast. So the idea now is gonna be to partition things into concentric circles. Right, if there's something in the smaller circle, that things, the sizes of those groups can only grow at a specific rate. Right, so there has to be like a pair of two consecutive circles where this ratio is gonna be somewhat good, right? Like something like n to the 1 over t, if I have t concentric circles. Right, if I knew which one, right? If there was someone who told me that, independently of every randomness I use, that would be great, right? Because then I could run their framework, their algorithm to output something from one of the circles inside the bigger circle, and output something uniform from that circle. Right, so this would give an overhead of only n to the 1 over t. And the other problem is, we would have to decrease C prime, it would be smaller, right? We would have multiple C primes which are smaller before we get to the full C. So this is gonna become smaller, right? So the problem is, which pair of circles to use, right? So that's kind of a tricky question, right? Because adversary, we can assume the adversary is probably gonna learn which group I sampled from, and like thresholding. Like trying to run all of them and maybe thresholding which one you use in the end, which outputs first, something could unfortunately reveal something to the adversary, right? So the idea is to, again, for each pair of concentric circles, to have like square root of q copies and of this fair near neighbor data structure. And then you look at them and you see for each of them if it's efficient, right? Like how many other things ended up in the same buckets, right? You can assume that everything that is close with high probability ends up in the same bucket somewhere as your query, but otherwise you have to be careful, right? It could be the case that some copies are bad, some copies are good. So then again, you use this 0-1 hiding framework, right? Use differential privacy or sampling, even, right? The simplest version to hide which one is the case, right? And then so basically you could output again this 0 vector, which pair of circles seems to produce good search data structures. It doesn't mean that the ratio there is small. It could be the case the ratio is really bad, but all the bad points are in like one place close to the outer circle, right? So like we don't guarantee that, but we can guarantee that it's likely gonna, with constant probability, it's gonna work fast. Right, and we have multiple copies, so then we pick one of them, we see which one's good for the specific query, and we just use that to output a uniformly random plot. Right, so without going into more details, the final query complexity becomes roughly something like this, right? Because rho is roughly this exponent is roughly 1 over c for L1, and it's roughly 1 over c squared for L2. So whichever of these two things you use, this rho is gonna simply become the kth root of rho. So this time the exponent becomes something like this, right? Like the exponent in the search, in the query complexity becomes something like this. So if your k is small, so you can make k bigger, so that decreases it, but at the same time it increases this one, right? But if your initial rho, if you are happy with having not so good maybe approximation, is large enough that makes the rho small, you can find some point, the right point that minimizes this constant, right? And in general, by having a sufficiently large approximation factor c, you can make this arbitrarily close to 0. This exponent in the query time. Okay, so I'm gonna skip detail, like talking about some more details. Let me just say that like if your space is non-dimensional, then you can use techniques of Chera, Panam, Jerry, and Delson, and it's possible to essentially do a union bound over all possible queries to ensure that every possible query is gonna work well. Unfortunately, this increases like the space usage by a factor of the dimension, right? So like if you are dealing with high dimensional data, that's not good. Yeah, let me just finish here.